So in this hour we're going to talk about geothermal energy. This is a topic that I actually covered during my doctoral studies here at EPFL, so it was a big part in the integration of geothermal energy, especially for the city of Lausanne. We had various projects with the service industriel of the city, so it's something I worked on quite a lot. I try to condense here in the next, let's say, 40-45 minutes, the key information about the resources, but if you want to go more in depth, we can have also discussion about this topic. So, in the title I wrote geothermal energy as the underground resource. So once I was at the seminar in Zurich by this one of the world experts, let's say from Stanford University of geothermal energy, and he defined it, the title of his presentation was the underground resource. Because he said correctly that the meaning of underground has two meanings in terms of geothermal. So the first one is that it's actually under the ground physically. And the second meaning of the word is that this meaning of underground, if you're passionate about movies, you might know what this thing is about, which is that people normally do not know what geothermal energy is about. They heard the name, but they don't really know. So actually, I would like to ask you, just by raising your hands quickly, if I tell you geothermal energy, what do you associate it for? So what kind of energy service do you relate to with geothermal energy? What can you do with it?
Heating.
Heating, okay. So how would you heat with geothermal energy?
I would say you send water into the ground.
Yes.
And heats up. Send into the houses.
Okay. So it's basically what we will call direct use. We just send some water down to the ground. We heat it up, and we heat the houses. Other uses.
Take the vapor from the ground. It's just some specific places. It's not everywhere, but then we can use the vapor for cycles.
Yeah. So this is what we will call electricity production with dry steam power plants. So if we are lucky, we are in a location where we have dry steam just popping up the ground, such as in Yellowstone, such as in Lardarello in Italy, such as in the Californian coast, let's say. We have this resource available. Okay, so electricity production. Something else you heard with geothermal energy? Okay, so the goal of this presentation of this lecture is to give you a brief introduction to geothermal energy, to show you what geothermal energy is about, and mostly to show you that actually geothermal energy can be used in a variety of different ways to actually supply almost all the energy needs that we have, depending on the depth at which we use the geothermal energy. So the goal here is to give you an entire overview of geothermal energy, not only focused on electricity production, which unfortunately I would say is often the only thing we hear when we hear the debate about how to use geothermal energy. You will see during the lecture that using geothermal energy for electricity production is not always the smartest thing we can do, especially in terms of exergy, let's say. And at the end of the lecture, anyway, we will have a part dedicated to how we produce electricity with geothermal energy, which used to be actually the only content of this lecture in the past. So, geothermal energy, as the noun says, derives from the Greek, so it's energy from the earth. So we have heat available from the earth at different temperatures, which actually comes from the formation of the planet, so for the original heat that we have from the formation of the earth, plus some continuous radioactive decay of material that we have at the center of the earth. And normally, when we talk about geothermal energy, we can only access a very tiny bit of the crust. So normally we talk about applications that will range between 0 and 10 kilometers depth in the ground. So in the previous lecture, we discussed about the notion of exergy. Just to recall it, we discussed that exergy is a better indicator than energy when we discuss about a heat source, because it tells us that the heat source has a different value depending on the temperature at which we have it available, okay? So you saw before with the lecture of Francois that when we have, for example, and we saw also in the first lecture about thermodynamics, when we have, for example, an ideal engine, we need two heat sources. If we have a hot source at higher temperature, so if the temperature here of the hot source increases, our Carnot factor, so the ideal efficiency of an ideal engine working between the hot temperature and the cold temperature will be higher. So having a heat source at a higher temperature will be better, we'll have a higher exergy content. So when we use the heat source to produce electricity, we will have a higher efficiency. And the previous lecture was about heat pumps. So what is a heat pump? The heat pump is exactly the reverse cycle of an ideal engine. So it's when we give work in order to increase the temperature, to either heat something at a higher temperature or to cool something at a lower temperature. Again, also in the case of a heat pump, if we have a heat source, let's say you want to heat your house, the highest is the temperature of the cold source. The lowest will be the work that you need to put in the compressor in order to, let's say, heat your house at a higher temperature, okay? So from the basic of thermodynamics that you reviewed here even before with Francois, having a heat source at a higher temperature will be something that will increase your exergy availability. That's why, for example, the lake, when it is at ambient temperature, is a huge source of energy, but you cannot do anything with it because it's at ambient temperature. There is no potential difference, let's say. So having something which is at higher temperature will have a higher exergy value. So now I would like you to try to answer this question. So we mentioned about the level of equality of heat. Can you estimate which is the second law efficiency of a gas boiler that you have in your house? And again, to answer this question, you can always log into that website with the same password as last time. And then you can leave it open because I will have another question later. So. Is anyone still logging in or answering? Don't be shy, you're around 60 in the class. That number should be very close to 60, unless you don't have a smartphone or a computer, which I assume to be very unlikely, right? Okay. So anyone still answering? So let's... I don't want to stop your motivation from answering, so please do. So let's see. Okay, so there is a lot of uncertainty here on the efficiency of this boiler. So probably some of you were thinking about the first law efficiency, which is the energy efficiency of a boiler. And that's something that's why, if you remember, I told you in the first lecture, first law efficiency, energy efficiency, is a normal way of accounting for efficiency, but it's not the best. Because, for example, you burn gas and you have around 90% efficiency. So actually, condensing boiler can have efficiency higher than 100% because we look at the lower heating value. That's something you had in the combustion lecture. So the first low efficiency of a boiler is actually around 90%. You burn the gas and you have around 90%, 100% efficiency. But the real efficiency of a boiler, so which is, let's say, the second low efficiency. I see someone happy there. So the actual efficiency is around 10%. Why that? Because what we are doing there is that it's true that we have a 90% efficiency in the first low, but we are using the temperature of the flame of natural gas. When we burn gas, we go up to 1,500, 2,000 degrees. So we have a very high exergy level content. The Carnot factor is 83% or something like that, even more, 88 I think. And then we use it at ambient temperature. So we destroy a lot of exergy that we could have used, for example, to produce electricity and then cogenerate to produce heat, okay? So when we have heat at very high level of temperature and we use it to heat a house, we are destroying a lot of exergy. And that's why geothermal heat is very clever to use, because this is a study in the US that shows at which temperature we normally need the heat in a house. So normally in houses, here actually it looks at the entire thermal energy demand of the US. You see that most of our heat needs are around 40 to 60 degrees. So exergy tells us that it is very, let's say under the exergy point of view, it is very inefficient to use a gas boiler to provide heat at 40 to 60 degrees, okay? And that's why geothermal heat is interesting. So to introduce why geothermal heat is interesting, let's try to answer this question again. So let's say we go outside here, outside EPFL, and we dig a hole of 1 kilometer, just right below EPFL here in Switzerland. So we're not in Iceland, we will not find dry steam and so on. But what is the temperature you would expect to find when we get to 1 kilometer depth below EPFL? Okay, so let me close this one as well. Okay, so 44% of you is correct. Roughly, this is the concept that is interesting, that we normally use for geothermal. So when we look at a given place, we have this concept which is called the geothermal gradient. The geothermal gradient tells us how much the temperature of the Earth, let's say of the Earth, increases with depth. Normally, on the European continental area, we have something in the order of magnitude of 30 degrees per kilometer. So if you dig a hole 1 meter just below the ground, normally 1.5 meters, you find 10 degrees, normally, quite constant over the year. And then after that, you have to add 30 degrees for each kilometer, okay? So in Switzerland, if we are at 1 kilometer, we will roughly be at 40 degrees. And then it will be more or less linear for the first, let's say, 10, 20 kilometers of the Earth's surface. Of course, if we have volcanic activity, tectonic activity, or something else, as we might have in Iceland, in the Yellowstone, in these areas of the world where we have steam available, then we might have something higher. So let's look at what we use geothermal energy for. As I told you before, so some of you mentioned the fact of directly using the heat for heating a house. Some of you mentioned electricity production. Actually, if we look, it depends, what we can do with geothermal energy depends at the depth at which we are. So, if we are, let's say, up to 300, 500 meters, what we normally do is that we use the advantage of having a relatively high and constant temperature over the year in order to use geothermal as the hot or cold source for a heat pump. So if we want to heat during winter, we have a very high temperature source during winter. If we want to cool, we can directly circulate the cold water through the pipes, and we have what is called direct cooling, thanks to geothermal heat. And this is the most standard application, and also, as you'll see, the most used around the world today. And the principles that apply are the same that Francois showed you before. So using a heat pump with geothermal energy will allow you to have a very high coefficient of performance, so the COP. If we go at higher temperature, at lower depth, which means we go between 1 and 4 kilometers, then the temperature will increase. And it will be between 40 and 100 degrees or something like that. So, as you saw before in the graph I showed you, this means that at that depth and you have more or less the temperature that you need to directly heat your house. So at this temperature, what you normally do is that you have direct heating for buildings, or you could also do cooling in this case, because there are some kind of heat pumps that Francois briefly mentioned before, which is called absorption heat pumps, that work with the principle of using heat, and they have a coefficient of performance of around 1.5 or 2. So you could also use these kind of systems. If you go at higher depth, then you can use the heat at above 100 degrees, let's say 150 degrees to 100, and you can produce electricity and cogenerate, okay? So if you look entirely, based on the depth at which you are, you can do a lot of things with geothermal energy. Actually, you can do heating, cooling, electricity production, and supply process heat to industry. So when you hear the debate about producing electricity with geothermal, it is not the only thing you can do. And actually, under the exergy and the point of view, is actually not the energy efficiency also. It is not the smartest often, because if you think about it, I told you before, when you burn gas with the boiler, you have a lot of exergy destruction because you have a lot of delta in temperature. When you use geothermal, actually, you just go down as much as you need to harvest the heat you need to heat your house. So exergetically, and also energetically, is a very efficient way of using the heat. So let's look at today what geothermal is about. So if we look at the entire world energy consumption, we see that in terms of electricity, we have the equivalence of 12 nuclear power plants built. In terms of heat, we have around 70 gigawatt installed. So if we look at the numbers, if we compare the total amount of electricity and heat produced by geothermal today, it is still pretty small. It's in the order of magnitude of 0.2% of the entire global final energy consumption. And electricity is mostly concentrated in areas where there is dry steam available, so very good resources, such as, for example, Iceland, the various parts in the US, the natural parks and so on. Italy is actually the highest installed capacity in Europe, because there is an area in Tuscany where the geothermal gradient is really high and you have dry steam available. And when we talk about heat, as I told you before, the most used thing we do is we use the heat for driving geothermal heat pumps. If we look in Switzerland the share is a bit bigger. Geothermal covers about 1% of the final energy consumption. There is no electricity production, but the heat, so the use of geothermal heat pumps is quite broad, and actually it is growing quite a lot. Especially, I've been working with in a couple of projects in Lausanne and in Geneva to make use of the aquifers for direct heating of the houses. So there's various projects you hear in the press that there's quite a lot of installations that are starting. And there is actually one project, the first project for electricity production in Switzerland is in Lavey. You might have been there for the Thermabus. And there they will drill around 3 kilometers and they will have cogeneration of heat and electricity. So they will produce electricity, and with the waste heat they will give heat to the houses. If we look at the electricity production, as I told you, we have about the equivalent of 12 nuclear power plants installed worldwide in terms of geothermal heat. They are increasing at a rate of about 2 gigawatt per year. And the first power plant was built in 1911 in Italy. So actually this was the picture here is the first ever installation that was done with geothermal energy, is when they used the dry steam to just produce electricity for lighting a light bulb. So this picture is from 1904, is the first demonstration that we could produce electricity with geothermal energy. And if there are some countries that rely on geothermal almost entirely, in Iceland, geothermal makes overall about 68%, I think, of the entire energy consumption of the country and 90% of electricity. And there are also other countries that are heavily dependent on geothermal. So, again, you might remember from, I think it was the World of the Euro Cup, they made this graph of how the Iceland team was selected. So you see that the earthquake surveillance and volcano surveillance is an important activity in Iceland. This means that the reason why these places have a lot of geothermal today is because there is a very good potential because they have dry steam available at high temperature, volcanic activity, and so on. So let's look now at the resources. So what kind of resources do we have available? So usually we make a distinction between different resources based on their characteristics and so on. The first ones are what we call hydrothermal resources. So hydrothermal resources are the ones that we find, for example, in Iceland, in the US, and these other places, is where we are lucky, let's say, and we have very high temperature steam available very close to the surface. So these are what is normally, they are very location dependent. They are normally located close to tectonic plates and so on. And let's say they are the only ones that are very cheap to run because basically you just have to have a hole, and there you have dry steam and you produce electricity. So these are the most common geothermal sources we still find today. Then, if we are in countries like Switzerland, when there is no any particular geology that favors geothermal, in these countries we can have our system, but we need to drill, and we need to drill as deep as we need in order to produce electricity or to have the heat. So often, there is this kind of system that you might have heard. There was one in Basel and one in St. Gallen of experiments to have enhanced geothermal systems. What you normally need to do is that you need to drill quite down deep in the earth and then use water at high pressure to create permeability, so to be able to circulate the water and to obtain then the heat above the ground. And then another resource which is interesting, normally, especially in Switzerland and other countries, is what is called deep hydrothermal. Deep hydrothermal basically means that you have an aquifer. So you drill down in the ground, you find water. This water will have the temperature based on the geothermal gradient. So for example, under Lausanne there is an aquifer, a very big aquifer, which is called the Malm aquifer. It's about 1.5 kilometers deep and it has a temperature of around 50 degrees. So these kind of resources are also very good because you have already water. You don't need to inject it. You can just basically drill and pump it up, and you have water available at that temperature. So, as I told you before, hydrothermal resources are very location dependent. So it means they are located in particular areas in of the Earth. So you just have basically to be lucky to find them where they are. Instead, there are other technologies, such as heat pumps and enhanced geothermal systems, that do not really depend on the location. And actually, this is the current trend worldwide, as you see in this sentence down here, that there is a natural progression to use from the use of hydrothermal resources, which are high quality and very rare, to the use of lower quality, but everywhere found resources. So for example, in Switzerland, you cannot do, of course, hydrothermal because you don't have any steam available on the ground, but you can use heat pumps and you can use enhanced geothermal systems, and they have a very big potential, let's say. So here I just report some breakdown of the cost of the drilling, which is of course the main problem and the main cost with geothermal. Just to give you an order of magnitude, in Switzerland, the order of magnitude was that there was, from historical data, is roughly $60 million to drill a 6 kilometers well. In the example we had in Switzerland, it costed around 21 million to build the well in St. Gallen. And the cost and the technology is basically the same you use for oil and gas, with the only difference that here you just put water inside. With oil and gas, you normally look for, of course, these other resources. If we look at the potential estimated for the future, you see that the estimated technical potential is very, very high. So the amount of heat that is available in the ground is extremely high. From this estimate that I report here, it's bigger than the total world energy consumption. If we look at what is forecasted to be, so the International Energy Agency forecasts that around 3 to 4% of electricity and heat will be provided by geothermal by 2050. But as you see, the potential is much bigger than that. So it's just a question of choice and implementation, let's say. And another characteristic is that it is a typical baseload technology. So compared to, for example, wind or PV, geothermal doesn't fluctuate over the year. So when you have your power plant or your heating system installed, it will run basically the entire year constantly, which is a difference with the other geothermal resources. And this graph here shows you, let's say, if you are in a location like Switzerland, so without any particular favorable geology, the kind of technologies you can use are heat pumps, usually at around 100 to 200 meters. You can use deep aquifers, as I was telling you in the case of Lausanne, or you can go down deep and drill at higher depth, like 5-6 kilometers, and you can have enhanced geothermal system, like the ones that they built and tested in St. Gallen and in Basel. And the future potential for Switzerland is forecasted that, so in Switzerland actually, when we talk about geothermal, we still mostly talk about electricity. So the plan is, in the Swiss energy strategy, is to cover around 7 to 8% of Swiss electricity with geothermal by 2050. Actually, as I told you before, it would make more sense probably to focus more on heat production for geothermal, but the debate in Switzerland has been mostly about electricity, so here I report to you the data that we have right now for this reason. And again, I was telling you, the forecast can be around 3-4%, but just remember that the amount of heat that you have available, so here for example, I calculated, actually I took from a report, if you take the amount of heat that is available in a 1.5 kilometers thick layer below Switzerland and you cool it down to 20 degrees, this is the amount of energy that you can extract. And you can compare it to what is the Swiss annual electricity consumption. So the potential you have down there is pretty big, and it's a matter also of a choice, the choice of using it or not. So now I pass to geothermal power plants. Yes?
I have a question. What is the lifespan of one geothermal?
So geothermal wells normally work for around 25 to 30 years. Because if you look at the heat flow that you have from the earth, the heat flux that you have from the earth, the natural heat flux, it is lower than the flow that you have from a geothermal well. So you gradually cool the ground, and normally when you have drilled one hole, you have it for around 30 years. That's the standard, let's say. Do you have other questions up to here? And then I pass to the power plants. Okay, so this last part of the lecture just mentions how do we produce electricity with geothermal heat. So as I told you, these are what is called high enthalpy application. It means that we have, if we don't, in Switzerland to do this, we have to drill quite deep, so let's say around 5 or 6 kilometers. And normally we can do it with, let's say, systems such as enhanced geothermal systems. But remember, keep in mind that even if now we talk about electricity, do not forget that the heat can be also used directly for industry and for directly heating the houses, for example. So, what is the efficiency of a geothermal power plant normally? So, if we have an extraction temperature and the reinjection temperature of a geothermal well, then the amount of heat that we extract is given by the mass flow times the Cp of water times the difference in temperature, as you know. And the first low efficiency is calculated with the usual formula, and usually it's quite low. You can expect to have a first low efficiency of around 10 to 15%. The second low efficiency instead, which looks at how well you are building your system based on the temperature levels that you have available, is usually quite high. So you can easily reach efficiency of around 45–50%. And you can also use geothermal heat in so electricity production with cogeneration, which means that if you have a temperature high enough, you can first produce electricity and then cogenerate, as you saw in the last week lecture with Francois, in order to also produce the heat. So again, based on the source that we have available, we have different types of power plants. The most classical one is the dry steam power plants, such as the one we have in Iceland, for example. So it means we have dry steam available, and we directly expand it in a turbine, and then we reinject it. So this is the most simple kind of power plant, and it's about 27% of the worldwide installed power. If we're less lucky, so we don't find directly steam from the ground, we find a mixture of liquid and steam, then we have what is called flash power plants. Flash power plants use a flash drum to separate between liquid and steam. And then, of course, the liquid is reinjected into the ground, the steam is expanding in a turbine. And this normally is done in one stage, so this is called the flash steam power plants in one stage, or in two stages. And these are, the sum of the two, they are the most diffuse power plants. And then you have binary cycles. The difference is that in binary cycle you have two different fluids. So you have the geothermal water that exchanges with another fluid for the cycle, usually an organic fluid. And that's, for example, the one you had in the first exercise in the first lecture, if you remember. So you have, usually it can be toluene or R134A. And these are very good for low temperatures, okay? And then you can also have other hybrid power plants that we'll see quickly now. So, the single flash power plant is, as I said, the most common one. It covers about 43% of the installed power worldwide. It's quite simple, the principle. You have, first of all, to separate the steam from the water. You re-inject the water into the ground, and you use the steam in order to be expanded into a turbine. So actually what you have is quite a standard ranking cycle, as you saw in the lecture on ranking cycles, in which you use the steam and you reinject the water into the ground. So the problem that you might have in this kind of power plants is that you're directly using the geothermal water. And so if you have impurities or gases embedded in this water, you might need to clean them or to remove them because it can damage the turbine or other components, or the condenser, for example, in this case. And the double flash power plant is basically, as you saw in the ranking cycle, if you do this kind of process in multiple stages, you can increase the efficiency. So it's basically a more complex system, which allows you to, it has the same or less characteristic of a single flash plant. You just do the flashing in two stages, and it is more complex to design, but it allows you to reach higher efficiencies, more expensive. It allows you to reach 15–20% higher efficiencies. And then, as I said, the last part of power plants, that is the one you can also use to do whatever kind of heat recovery from low temperature heat sources. So flash power plants is what you use normally above 150 degrees or so on. Binary cycles, as you see, they use geothermal water to exchange with another fluid, an organic fluid. And the characteristic of organic fluids is to, compared to water, they have a much lower evaporation temperature and pressure. So they allow you to recover heat from resources which have a low temperature available. So usually organic ranking cycles, they are not only used for geothermal. If you remember in the ranking cycle lecture, I told you that you use it, for example, in cement power plants, or when you have waste heat from whatever sources. It is quite commonly used for different applications. And the advantage that you have is that these plants, again, they don't have the same problem as flash power plants or so on, because you do not use directly the geothermal water, so you don't have all the impurities or the other things left in the gases. You don't have to clean the fluid. You have two separate systems, let's say. The problem is that normally organic fluids are flammable. So, for example, R600 can cause explosions and so on, so they need to be carefully managed. And the last cycle that I present you is a commercial cycle. It's called the Kalina cycle. It is very similar to an organic ranking cycle. The only difference is that it uses a mixture of water and ammonia. So the advantages of this cycle is that ammonia is a known fluid, is widely available, it is non-inflammable, it has the disadvantage of being toxic, so of course you have to take care about leaks and so on. The advantage of having two fluids together is that you can increase the efficiency because you reduce the exergy losses, right? Because as you remember, as you know, water and ammonia, if you take them alone, they will have an evaporation at constant pressure and temperature. But if you mix the two, the curve of the evaporation will have a certain incline, and this will allow you to follow the decrease in temperature of the geothermal resource, making the area in the temperature enthalpy diagram of the exergy losses due to the heat exchange quite small. So this is simply an evolution of the organic ranking cycle, which allows you to have some advantages and an increased efficiency. And then you can have other applications. So for example, normally what can happen is that you can have a flash cycle at a higher temperature, followed by a bottoming ranking cycle at a lower temperature. Or if you have geothermal heat available in, for example, close to where you have a gas turbine, then you can use, or another ranking cycle, you can use the geothermal heat to preheat the water that you use in these cycles, and then, of course, increase the efficiencies of these cycles. So these different combinations, as this one here using a gas turbine, they are what we call hybrid cycle, which combine different sources in order to increase the overall efficiency. And just to conclude, let's say at the cost data, roughly, as you remember, as I told you before, flash cycles are more common at higher temperatures. They are cheaper to build, and they are a bit bigger. If you go towards organic ranking cycles and Kalina, due to the lower efficiency that they have, they work at lower temperature. They are less expensive. They are more expensive, sorry, and they are smaller in size. Okay. So just to conclude, if you look at the prices that you have, so these data are a bit old. You didn't find an updated version of these ones, but due to the different efficiency, as I mentioned you before, when you use geothermal heat to produce electricity, you normally have a levelized cost of electricity which is higher. If you use instead geothermal heat to directly use it for heating purposes, you have a cost which is very competitive also with whatever other source you use. So you see that the price, for example, for geothermal heat used for house is very similar to the prices that we have today for natural gas in the market. And today the prices that we have for natural gas are very, very low. So it means it's a very competitive way of supplying heat, for example. So just to recap, what we talked about is that the advantage of geothermal heat is that we can use the exergy. We have a very exergetically efficient system. When you hear talking about geothermal, do not only think about the electricity production, but actually mostly focus on the advantages that you have for heat. And the characteristic of geothermal is that it is a baseload technology. So compared to other renewables, it has the characteristic of being a non-seasonal resource and not daily variable resource. So it can be used for baseload heat and electricity production. In terms of resources, we are moving from a situation in which we were only using resources which were which were available at a in very specific locations, such as Iceland or this kind of places where we had dry steam available, to resources which are more widespread and more ubiquitous, let's say. And we have a very huge potential, but we don't have to forget that there are also technical difficulties related to that, especially to the drilling. So I didn't tell you much in detail about the project in St. Gallen and in Basel, but so is any one of you from this area actually? From St. Gallen. So for different reasons, actually, both projects ended up being stopped. In St. Gallen, it was the case in both cases it was due to earthquakes that were caused. Actually, under the technical point of view, both the projects went really well, especially the Basel one. They went down to 5 kilometers and they found exactly the right temperature and so on. It was mostly, I would say, a problem of communication in the case that in the city there was a big alarm when there were earthquakes that are actually expected. So it was mostly the effect of communication to the people. And then they had to stop the project due to the fact that the public opinion was worried about these earthquakes, which actually did not go above what was forecasted by the drilling. And but so there are indeed problems and challenges when you have to drill at a very high depth. That's for sure. And about geothermal power plants, as I told you, normally if you want to produce electricity, you have a quite low first low efficiency, but a quite good second low efficiency. And I leave you in the slides an exercise that you can do later. There's also the solution later, which shows you an example of a system which was built in France, in Alsace, in Sous-Forêt, and where actually you can calculate all the performance of this system, and is a kind of similar little calculation that you might find as well at the exam. So with that, if you have any questions. Otherwise, see you next week.